Greetings and salutations, magical chemists. Let's talk about tasty and thirst-quenching hydrates. A hydrate is a pure substance that is often ionic, which contains a fixed composition of water molecules embedded into its crystalline structure. These water molecules are known as waters of hydration. If you apply heat to a hydrate, that will drive off the water molecules, and the solid that remains behind is called anhydrous, or without water. By measuring the mass of the water removed, we can determine the ratio of water molecules to the salt, which allows us to find the formula of the hydrate. But before we dive into the math for hydrates, I want to talk briefly about the language we use to discuss hydrates. The hydrate is what we call the compound when it has the embedded water. When we heat the hydrate, you are not evaporating the water molecules, because evaporation is specifically a liquid going to a gas, and you'll see when we do our hydrate lab, hydrates are usually solid. So specifically, water molecules are being driven off. And after you've driven off the water, what's left is called the anhydrous salt. It's not a hydrate anymore. All right, let's look at some tasty hydrate mathy math. There are two calculations that commonly come up when working with hydrates. The first is figuring out the percentage of water in the hydrate. Well, that's just a, simple percentage calculation. You get the mass of all the water, and then you divide it by the total mass of the hydrate, boom, times 100%. Just like all the other percent calculations we do, this is not on your formula chart, so you just gotta know how to do this. The second calculation is determining the formula of a hydrate. So let's look at that step by step. They call it gravimetrically determining it. Well, it's just a fancy way of saying we're doing it by mass because, we're weighing stuff. The first thing you have to do is determine the mass of water that has left the compound, that you've driven off, so to speak. And you convert that mass to moles. And then you take the mass of the anhydrous salt, or the anhydrate, and you convert that to moles too. Last but not least, you find the water to anhydrate mole ratio. That process is going to look almost exactly like finding an empirical formula, but with one key distinction. You are not allowed to multiply till whole. That's because the mole ratio of the anhydrous salt must always be 1. There's one formula unit of the salt for however many number of water molecules. Once you know the mole ratio, you know the formula, and that's it. So let's go ahead and try an example problem. This set of data is fairly typical for hydrate data. You have the mass of a container, in this case a test tube, the mass of the container with the hydrate in it, and then the mass of the container with the anhydrous salt after you heated it and drove away the water. So first, we want to figure out how much water was lost. There's actually a lot of ways to do this, and it doesn't matter which one you use. So look at the data and try it, and when you're ready to check your answer, unpause the video. Well, this is just simple subtraction, right? You want to see how much water was driven off? You look at the mass when it had the water and the mass after the water was gone and subtract them. And now we want to find the percentage of water in the original sample. Well, to do that, I have to know the mass of water lost, which I have, but I also need to know the mass of the hydrate itself. So I have to go ahead and subtract the mass of the test tube from the mass of the hydrate. Once I have that mass, it's easy enough to throw the data into the percent calculation to find the percentage of water. So this hydrate has a relatively small percent water, just 15%. So next, we need to calculate the number of moles of water that were lost. Well, that's easy because we already know how many grams were lost. So after dividing by the molar mass of water, I can see I have 0.019 moles of water in that original hydrate sample. Next, we need to calculate the moles of the anhydrous salt that remain. You should totally try this on your own. There's nothing new in these calculations. So see what you think, and when you're ready to check the answer, unpause the video. Well, before I can find the moles, I of course have to find the mass, and then use the molar mass of just the anhydrate to convert to moles. And after that conversion, now I know how many moles of BaCl2 were in my original hydrate sample. So my very last step is to actually determine the formula for the hydrate itself. And remember, this is the process that looks like you're doing an empirical formula calculation, because it really is the same thing. Of course, instead of having elements, now I'm looking at the ratios of these two compounds, the BaCl2 and the H2O. And honestly, it's a little bit easier because I'm not starting in grams. I've already done the gram to mole conversion, so I'm just starting with my mole ratio. I just need to simplify it into whole numbers. which I do by dividing by the smallest number of moles. And so I can see that I have a dihydrate. There are 2 waters of hydration for every formula unit of barium chloride. Remember, it's basically a dot in between the ionic compound and the number of water molecules to show that they're complex together when we're writing the chemical formula. And in the naming of a hydrate, all you do is you name the ionic compound first, barium chloride, and then you do use a prefix to tell you the number of water molecules in your hydrate. And that's it. That's really all the math you have to know. However, determining the formula of a hydrate is an experimental method, so it's important that we actually talk about possible errors that might come up when you're doing a lab of this nature. Well, you have to heat your hydrate to drive off the water, but you can't overheat the hydrate. If you have excessive heating, it can cause the dehydrated sample to decompose, which will often release a gas. In that case, not only will the water be driven off, but you're also losing gas from the decomposition. So it will look like more water was lost than really was. So in that case, you're going to get a calculated percentage of water that's going to be larger than the actual percentage of water in your hydrate. Now, if it's particularly humid out, which, it happens, in that case, you have to heat up your sample, drive off the water. But then, if it's too hot, you have to let your sample cool before you can measure it, and during that time, it's possible for it to suck up moisture straight from the air. And in that case, technically, it stole some of its waters of hydration back. So your calculated percentage of water will be smaller than the actual percentage of water in the hydrate. Now, the last and easiest to avoid error is if your hydrate was not heated to what they call a constant mass. And in fact, that was an error in the data that we looked at in our example problem on the previous page. Here they're giving you the data before heating and after heating. Well, how do I know I heated it enough? How do I know all the water's actually gone? What you do is instead of just heating it once, you heat it, measure the mass, and then you heat it again, and again, and again. And of course, you're measuring the mass each time that you heat it. Once the mass remains constant, aka you heat it and the mass doesn't change, well, that means all the water molecules must have been driven off. So if you don't heat to constant mass, and check yourself, honestly, you probably didn't drive off all the water, so of course your calculated percentage of water in the hydrate is going to be smaller than the actual percentage of water. Now let's try a couple of example free response error analysis problems. These are very common AP free response problems, so it's essential that we understand how to answer them. So take a moment to read this prompt, and when you're done, unpause the video and we'll continue forward. Okay, so if you notice in this particular problem, a student wants to experimentally determine the waters of hydration of this particular hydrate, but they know what the formula is supposed to be. The formula is supposed to have 3 waters of hydration. But after the student does the lab and they collect data and they do all the analysis, well, she derived the formula as only having 2 waters of hydration. And you're asked for 2 things in your answer. It says both provide a reasonable explanation for would have caused that error and explain how this error would have led to that student's results. It's essential in AP free response to be certain you know what question they are asking, because so many awesome chemistry students in the past have been tripped up because they answer a question very well, but it's not the question being asked. So there are 2 parts to the explanation we have to hit. Hopefully you noticed they said that this student, when they were heating the hydrate, they didn't really specify anything about heating it. They're just like, well, she heated it and then she measured the new mass. I personally believe it's unlikely that all of the water was driven off after one heating. And that's the most common mistake with hydrates. So that's the one I'm going to choose for my explanation. Of course, if you don't drive off all the water, notice, didn't say evaporate. We're talking about driving off the water for hydrate. Very dramatic. Well, if the water wasn't driven off, then the measured mass of what's supposed to be the anhydrate is going to be too large because it still has water. And if your anhydrate mass is too large, when you subtract the difference from your original mass, the calculated mass of water in your formula, of course, is going to be too low. You didn't drive it all off. Okay, so we've explained the error that might have caused this outcome, but we haven't completely answered the question. Here's our explanation, but remember there were two parts to the question being asked. They also wanted to explain, okay, but that's great. How did this error affect the results? Well, so there's just like one little last thing we need to throw in there. We'll be like, okay, the calculated mass of water is too low. Well, that means, of course, their experimentally determined hydrate formula shows less waters of hydration. And then we're done. I do want to point out, you may look at that and be like, oh my God, so many words. You're not required to write in complete sentences. This is not AP Bio. You will not have points deducted if you do this with bullet points or incomplete sentence fragments. Doesn't matter as long as the information is on the page. I just tend towards sentences. Okay, there is a second free response practice problem, and guess what? You're going to try it. It's going to be ever so much fun. So go ahead and try this problem. And please, oh please, actually write out a tentative explanation. And then when you're ready to check your explanation, go ahead and unpause the video. Okay, in this problem, I'm sure you noticed that the second student repeating the experiment, well, they decide to heat the sample multiple times, which is always a good idea when you're heating a hydrate. And they're going to do it over a higher heat. He wants to be certain he's driving off all the water. But I'm sure you also noticed that when he did that, he got 4 waters of hydration when actually there are only 3. So the question here is a little less specific than in the previous example, because it just says, okay, well, explain what error might have caused this. I did the last one in complete sentences, so I'm going to go ahead and show an example of how you could answer this with bullet points, and either one is equally valid. Whatever is easiest and most natural for you that can communicate the required information, that's the winning choice. Okay. So since it says explain what error might have caused this, we have to make sure we mention, well, he heated it multiple times at high heat and what that would cause. And why do I think that that's the error? Well, doing that might have caused some of the anhydrate to decompose, releasing a gas. So I'm going to go ahead and use the mathematical implies sign. So the student heated the sample multiple times at high heat, implying some of the anhydrate might have decomposed, releasing a gas. And of course, if we decompose the anhydrate releasing a gas, your calculated mass of water is going to be too high because the mass of the gas is included when you calculated your change in mass. Notice that I am totally using some symbols instead of words because I'm trying to be efficient. I just need to get the correct information down. So I didn't write out at, I used the at sign. I didn't write change in, I wrote delta. And that's okay. Chemistry people are math people. You could totally use your math symbols as part of your answers and we can follow you. Now, you might be thinking, okay, don't I need my summary thing? Like, okay, thus the student's experimentally determined hydrate formula shows more waters of hydration. I claim no. Here's why. The previous problem asked us to explain how the error affected the student's results. And results, of course, were the formula, the waters of hydration. This prompt just said, explain what error might have caused this outcome. It was a little less specific, so my answer can be less specific. And that's important to note because you don't want to waste time writing more than you have to. Now, you might be wondering, what if I did write that last sentence? So the, determined hydrate formula will have more waters of hydration. You're not wrong. You don't lose any points, but you have lost a little time. And if you wrote your last sentence, but you were kind of frantic because you're running out of time and you flipped it, you would just negate all the right things that you did. So free response can be very tricky. It's key to make sure that you are identifying exactly the problem asked and no more. All right, that is it. Thank you for playing with the tasty and thirst-quenching glories of hydrates.